Alright, so we've made it this far into the class, and now it's time to discuss quantum computing. Ooh. So here, you'll see Google's quantum computer right here, and it's cooled in, it's actually super cooled in this architecture tower here that you see to your right. But let's move ahead. So, what is quantum computing, right? We've previously looked at and explored the topic of quantum computing in IBM Qiskit, and if you haven't had a chance to look at Qiskit, I encourage you to look at this textbook. It gives you a quick, too long didn't read or TLDR overview of what essential quantum computing topics are so that you are quantum literate and that you may explore it from a very knowledgeable intro level standpoint. Okay. So after that, go ahead and answer these questions in the class discussion canvas. You'll have to explain your thoughts on the modules inside of the Qiskit from IBM, and then bring up two applications of quantum computing, and then consider what considerations we might have to take when working with a quantum computer as opposed to a regular computer. So our next question talks about RSA encryption versus quantum processing power, and it asks, how will quantum processing power impact RSA encryption? So RSA encryption is standard encryption, and it encrypts everything from passwords to credit card information. So as you can imagine, people with a quantum computer might be able to crack all of this. So how do you think our world might change? Will we have quantum cryptography to counteract this? Who knows? Leave your thoughts. Here is more background. So let's flesh it out more. A quantum computer has exponentially more processing power compared to a traditional computer. For example, Google's new quantum computer is 158 million times more powerful than the most powerful supercomputer today. So yeah, it's so if you don't know, classical computing is based on electrical circuits with a bit or an byte being in a single state, 0 or 1, or on or off at a given time. But in the world of quantum computing, we have quantum mechanics such as superposition and entanglement. This is a phenomenon where it's possible to have more than one state at a given time. And here I've given you a source, which is a Medium article, and it talks about Google's new quantum computer. Okay, so how might data encryption and storage be different in a quantum environment? So here's some background. I'll just give you the answer here. A quantum computer operates differently compared to a traditional computer. So by having a quantum processing unit instead of a CPU, a central processing unit, it stores information along a series of interconnected qubits by means of quantum entanglement rather than a traditional binary bit, which we've seen in the binary numbers video at the beginning of this course. My fifth question, how might time complexity be differently measured in a quantum framework? So how do you think quantum entanglement might affect big O? What might runtime complexity look like, right? So food for thought. And six, I think this is one of my favorite questions. Why is data stored in binary base 0 and not hexadecimal base 16? And this is a follow-up question. How might data storage look like if files are encoded in base 16? And I'll ask you another question, which I have regretted to put here, but how might data be stored with qubits? That's very interesting, right? Quantum entanglement, superposition. How might it be stored in a qubit? All right, that's it for this session.